Alright, bitches. Hello from your favorite artist electronist, Mr. Q12 here. And the experiment continues with a little bit of upgrades and some other weird stuff related to switching Mosfet that I'm having there. So let me show you the upgrade for now. As you can see here, my little transformer that I'm having here, my scrapped transformer, is having only one bridge rectifier now. This is the circuit here, the circuit diagram for exactly for the wiring that is happening here. Actually, a friend from AAC solved this little detail for me, because I was literally not thinking in depth to this regulating issue that I'm having here, and he did put a little bit more thought on it. I like to say that I personally slapped, you know, when you are slapping like that, when you are slapping like that, those two bridge rectifiers, I literally didn't think too much. I just slapped two bridge rectifiers there, and that's it, you know, without too much thinking. Yeah, let's say it was a little bit of mistake from my side and from my part. And one of my many friends from AAC forums, he catched that mistake and he solved it for me, actually. So this is not my thinking, this is not my logic, this is someone else's logic. And this is the circuit here. Let me explain it a little bit. This point here is the ground that is coming out from this bridge rectifier, and you can see it here. Actually made a ground there. I put the sign that is the ground, but then I continue it through that little arrow of the ground. I continue it here. Well, this is the actual line that you are seeing here. I wasn't sure if I will drag a wire from this point somewhere else, so that's why I put this extra line here. But it's actually this end of this bridge rectifier that you are seeing there. This is a little bit unusual, well, at least for me. To be sincere, I didn't work that much with 2 voltages from a single transformer, and this is probably the first time. Or maybe I did work, but I didn't care or didn't pay attention too much what's inside, how is the wiring for a 2 voltage output isolation transformer, and how to rectify those 2 voltages that are coming out. So that's a little bit of first for me. So after changing with this circuit that you are seeing here and this wiring that you are seeing here, when I measured, actually both with my oscilloscope and with my digital multimeter, these values that you are seeing here actually are the values that I've seen on my oscilloscope. They are not the values that I've seen on digital multimeter, but digital multimeter is very close to these values. So my oscilloscope voltmeter is not completely in the agreement with my digital DMM digital multimeters. Multiple of them I tested, actually. Not that many. I tested only this one and this one. 2 of them, because they are good at measuring voltages, but their values were not exactly the same as what you are seeing there. That's a point that I want to specify. And these voltages are a bit higher in this configuration and this circuit that I'm having here than before, when I was having those 2 bridge rectifiers. Probably now is higher because when I was having those 2 bridge rectifiers, there were a bit more voltage drops inside the bridge rectifiers, and those voltages zoomed up, and probably that's my explanation, at least, why it was here it was 5 volts and here it was 10 volts. But I didn't measure these voltages with my oscilloscope there. Actually, I was having very high voltages on my oscilloscope with those 2 bridge rectifiers. What I did, I measured with only exclusively, actually, with my digital multimeter. It was exclusively with this little one. I did my measurements. What I want to underline here is that it matters very much with what tool you are measuring and with what tool you must continue all the measurements. The problem is being different between them, the reading of the voltages. It got me confused a little bit, and I will prove it in a second. So this is the experiment before this one that I'm making right now. You can observe these 2 bridge rectifiers. This is the measurement that I did in different circumstances. So right now what I'm measuring is the alternative between 2 points, the maximum actually between A and C here with red on the circuit diagram. You see, these are the maximum voltage from these 2 ends, and this is my oscilloscope. What is showing here, you see 30 volts peak to peak is actually going to positive 15 and negative 15 under the 0 volts line. You can see it here, and I'm specifying this little detail because we will see it later in my experiment from today. I was getting a sinusoidal wave, but it was not crossing the 0 volts. It was alternating, but in DC. And I really don't have a good explanation why I was doing it. I can only speculate, but not really a good explanation. But you will see later. But I'm showing this little detail right now when I'm probing this to output from the secondary points. Right? So 50 Hertz, perfect 50 Hertz, by the way. Very perfect 50% duty cycle, and time, perfect right on the 0 milliseconds. So this is perfect. It's a very good transformer. Like I said already, it's looking old, but it's performing like a brand new, very good transformer out there. Okay, so here these 2 points, I changed to this middle wire here and to the A and B in this point. So as you can see, this is the other wire that is coming. So this is alternative reading of the secondary coil. And here is the reading. Earlier it was 15 volts on the extreme, on the maximum, and now is half of it. As you can see, is 7 volts, and between positive and negative, when the entire swing voltage peak to peak is 14 volts. These two voltages summed up. The counter inside this oscilloscope is adding or taking a little bit from the perfect value that it should be. It was a 50 hertz, exactly 0.0, and this was exactly 50% duty cycle, and this was a perfect 10 millisecond most of the time. But here, my hand trembled a little bit, and I catch this a tiny little bit off values. This is not an issue, but you will see later why I'm specifying this. This is normal alternative voltage reading. Okay, now I'm doing the same reading that I did with the oscilloscope here. Actually, with this one, when I got this 30 volts peak to peak were positive and negative 15. I'm doing it with my digital multimeter, DMM, and you can see here the knob is pointing to 200 volts. Alternative is not continuous. This is the continuous side, and this is the knob here pointing here to the squiggly alternance. What I'm getting on my multimeter is 10 volts instead of 30, which is peak to peak, or 15 per phase. But this is not actually measuring the phasing. It's actually measuring peak to peak from A to C, and it should have been 30. For some reason, I'm getting this 10 volts or 11. Which is a bit weird. And now A and B also alternative reading. With this, I'm getting 4.8 instead of 7 that my oscilloscope was reading. So you see the difference between my digital multimeter and my oscilloscope. It's quite a interesting difference. Okay, so this is exactly like the ends that I tested with the oscilloscope. Exactly the same thing, but with different tools. So it matters with what you are measuring and with what you are continuing to measure along the experiment. You don't switch them willy-nilly. You have to stick with one. That's my point. All right, now we are getting into the DC reading or continuous current reading. I'm getting 4.8 and 9.7 here with the multimeter on the top one here. I'm showing all this for comparison with the one that I'm having right now on my table. And the lower one, I was getting 5 volts. So you see, it's quite a big difference. These voltages here are quite different from the ones that I'm having right now. Right now I'm having 7 volts here and 14 volts on the top. And this is the oscilloscope reading on directly on the DC reading. You see here 16 volts DC for this smaller one that should have been 4.8. So I'm getting 16 volts, a little bit crossing the negative rail there, and very weird waveform, extremely weird waveform. It shouldn't have been like this at all. And here on the top one, I'm still having that 16 volts on the top one. So these two voltages, when I'm reading them from my oscilloscope, I'm getting the exact same result, and also double the frequency is doubled here, and the duty cycle is a little bit higher. Than 50 hertz. And it's the same with the today readings. Here I was changing, you see here 5 volts per division, and here is 1 volt per division. Here I put the probe, 0.8 volts with this multimeter on this point and the negative rail. And here I was having this almost 2 volts, 1.9 volts voltage peak to peak. But you see this squiggly waveform, very close to 50 hertz also here. This was a very big question for me, why I'm getting these squiggly lines through when I should have a straight line here. But I'm getting this oscillating DC voltage. And here, I don't remember what I did. Probably I changed the division just to show how it's looking. Here is another interesting reading. Here I changed the capacitor. Actually, I put a 2200 microfarads here. And you see this, it transformed the line, the reading quite dramatically. You see, this is quite high timing. It's 10 milliseconds. But if I'm lowering the timing for the horizontal knob, it will change dramatically the waveform. Here at 10 milliseconds is quite higher timing. And you will see in the movie today. And these are the lines that I will speak about in my movie. And this is the first set of lines that I observed. And here, only by changing the horizontal knob of the oscilloscope, I got, you see, this is 20 milliseconds in the milliseconds range. And here is still in the milliseconds range, but it's lower. But you see how nice and interesting and very interesting waveform with those spikes to the 0 volts rail. So this is not between the positive and negative rail, like an alternative sinusoidal waveform. This is also sinusoidal, but is maintaining into the DC positive side. The minimum is 60 millivolts, almost 0 volts, a little bit over the 0 volts rail, and the maximum is 5.8 there. And the frequency is 1.2 kilohertz actually. It's a very good frequency. It's very interesting frequency. While here, you see the frequency is very low, very low. I'm not
completely. So these two images that you are seeing here, I'm using the exact same setup, the exact circuit and probing points. I'm only changing the horizontal knob of the oscilloscope from 20 milliseconds to 2 milliseconds. That's it. And I'm getting this very interesting reading on my screen. And I try to reproduce it today, but it appears that I'm getting these results when I was having these two bridge rectifiers. So this is very interesting, actually. A very interesting waveform what I'm having here. And that's it.
So right now this circuit got changed. Last time I was having this capacitor here after the resistor, and it matters. Unfortunately, this one single ohm and this capacitor, they're creating a filter for frequency. So having them inversed like it is right now, I got very different results than I'm having with this setup. I updated this circuit diagram with what I'm having here. So I'm having these two lines, power lines from my variable power supply. I'm keeping it at a fixed voltage of 10 volts most of the time. Like my friend from America who was doing his experiment at 10 volts powering the gate of the MOSFET. So I'm working on his steps as best as I can with the tools that I'm having here. So this 10 volts is powering this circuit, this entire circuit here, until the gate of the MOSFET, which is that one there, here, all right? And is pulsing the gate with 10 volts there, okay? And then this circuit here is this transformer, that bridge rectifier, this capacitor, this resistor, this MOSFET, and that's it. It's like a single line. I can cover like this circuit. This is the driver for the MOSFET, and here this line that you are seeing here, this is the, let's say it's the load line, is the power line. Unfortunately, I must specify now that this is not actually a power testing for the MOSFET yet. I'm only testing the functionality when this MOSFET is pulsed. So it is creating some very strange behaviors. Better say, is soliciting my power supply, this MOSFET, when it's switched at a certain frequency. And I got some problems, and right now I'm trying to understand and to deal with these switching problems that I'm having here, that are happening on this, let's say, power line. because this 1 ohm resistor, which is this big one here, it is after all heating up a little bit slowly, but it is reaching very high temperatures, and I'm stopping it quite often, and I'm making pauses to let it cool. All right, so this is exactly the positive wire that is coming out from this bridge rectifier, which is from this point here, and it's coming to this capacitor. This is the capacitor here, and I put here 1000 microfarads, but if you read here, it says 3300 microfarads. Another little detail about this circuit is where I'm putting the positive line, this red line where it is right now. And as you can see, it is here at 7.5 volts, and it is a wire here that is going back. So it's not coming directly from this bridge rectifier like it's here, because if it was coming from here, it was at a higher voltage, and now this red wire, I link it here at this 7.5 volts. And I'm also having this capacitor there on that line, which is this. In both cases, you know. I was thinking actually to add a switch between these voltages, but I will see about it in the future. So that's the presentation of the circuit that I'm having on my table right now, and the values and everything. And let's actually start doing some experiments. As you can probably see, my drain, so you see this is the drain here, this red wire of the MOSFET is not linked to this resistor. So this is the point where I cut the line between the drain and this resistor, exactly here. This is easier for me to do the experiments that I need to do, and you will see in a second. So right now it's 0, because this power supply is not doing anything. I will have to keep it out. This wire is cut out right now. So what I'm powering only this, and measuring. I'm measuring only this line until the MOSFET, until the drain of the MOSFET. So from here to there. Basically, what I'm trying to show you is what is happening when all this circuit is not on the same power line with this transformer. Let's see how this transformer is behaving. So right now, cut out from this switching circuit, the probe, I can put it here too. The negative is common for both circuits, for this and for this line. So this is the probe for the negative rail. Only the positive probe, I'm moving it around. Yeah. I'm getting a constant 7.5 voltage without this transistor MOSFET. And without the circuit, only on what you can see here. So you can see clearly that it is not alternating anything. When I'm switching from this horizontal, you should pay attention here, and also the line that I'm having there. So this is the minimum I can reach, 10 nanoseconds. It is already very constant, not ondulating, not doing anything weird. So let me get back. So now I'm changing from here, from this knob. I'm changing. Let me get back to in the range of milliseconds. It is not loaded with to anything. I should have put this end to the ground and actually measure the power that is consuming there. But I don't do it because this is literally 1 ohm, and it's like a thicker wire, and pretty much I'm shorting the power supply. And well, I don't want to do it this way. I should probably do it for a very brief time to actually read what is happening here, if it's any changes. So I soldered a black wire here. So from this point where they are interrupted. The drain is having no contact with this power resistor that I'm having here. So this power resistor, its wire should go to negative rail, which is this. So it should go like this. The drain of the MOSFET is this wire here, is not in contact with anything. So if I'm touching, you can see here this wire. If I'm touching this power, this is the power rail, this very big line that I'm having here. If I'm touching it like that and holding it there, so right now it's constant. It's not loaded with anything. And now when I'm loading it, I'm getting voltage peak to peak 2.3 volts, frequency 100 hertz, and a duty cycle of 54%. And timing is 5.4 milliseconds, switching or alternating. I'm not completely sure what is measuring there. 50 millisecond, 100 millisecond, like that. And let's see now. Yeah, it's still squiggly. 60% there, 50%. It should have been a constant 50% there. Because when I'm measuring with my oscilloscope, these two wires here, or that wire, but directly on the alternative, I'm getting a perfect, absolutely perfect 50% duty cycle here, and the frequency is a perfect 50 hertz when I'm measuring the alternative 7 volts. But right now is rectified, unfiltered with this capacitor. That's a bleeder resistor, a 10 kilo. You can see it here. This 10 kilo is bleeding this capacitor when it's unpowered. So right now, as you can see, is 7 volts. And when I'm unpowering this transformer, I take it out. Let me actually switch to be more like this. You see, you can see the numbers here to have a better update, you know. And you can see slowly this line is going down by itself. You see, 3.6, 5, 4, 3, 3, 2, 1, and 2 now, 2.9. Is it 2.9 and so on and so on. And this will go to the 0 volts rail because of that resistor. If I was not having this resistor, this voltage was not decreasing like it is doing right now. It was staying at that maximum 7.7 volts, whatever it was. It is fluctuating and is not constant. It is constant when it's not loaded, when it's only filtered with this very low, extremely low value resistance load, what I'm having here. So it's not really continuous. For some reason, probably is supra soliciting the bridge rectifier, and the bridge rectifier is not rectifying that well. I'm not completely sure why we are seeing those variations, that alternance. But that alternance actually is not positive and negative around a center line. It's actually alternating the positive line a little bit. Let me do the test again to confirm with you. So right now we have a 7.5. And now voltage peak to peak is 2.3, but as you can see, this V minimum is not going under the 0 volts. You know, is still positive. Is 1 volt positive, and that V max is 3 volts positive. So this VPP is between these two values, and is not like an alternative. Is alternating, but is a continuous oscillating voltage, and most probably is because of this very low resistance load that I'm having here. That's why I'm having this strong feedback from the transformer. This alternance that I'm seeing on my oscilloscope. It crossed my mind to change this load resistor that I'm having here, this 1 ohm. You see, 50 watts and 1 ohm. I was thinking to change it with something bigger, with 10 or 100 ohms. But I have at 10 watts. It should be relatively equivalent. The drop in wattage, but the increasing in resistance, it should be somewhat equivalent with this 1 single ohm resistor that I'm having here. So this is my biggest suspicion, is this extremely low resistance load that I'm testing. Literally, I'm testing the transformer itself, and I should actually feel if it's getting hot, but I didn't let it too much in function. I only tested it for a couple of seconds, not even minutes. So I didn't leave room for it to get hot. That's what I did here. So I'm kind of protecting it as best as I can. So the next course of events, let's actually test the switching MOSFET when it's linked to this resistor and see what is happening there. Now my circuit is exactly like here, so it's no separations. I didn't cut off any line, and it is exactly like you are seeing here. Okay, this is looking like a B, but it's actually a D from drain. I erased something there. Okay, so right now I didn't cut any lines anywhere, so it's exactly like it is right here. And is actually this transistor is pulsing, this load resistor and the power supply is pulsed along in the same time. And let's see what the oscilloscope is saying. When I'm powering this transformer, when I'm powering it, we will see the oscillogram, what it's saying. Ta-da! It's saying not very clear frequency and duty cycle. 52 is undecisive, 100 and something hertz, 100 or 128 hertz. It's fluctuating. 52 or 66 hertz is when it's catching the line, probably when it's reading it. Plus probably a little bit of spikes here and there. And this is with this capacitor, with the last one in the list, with 3,300 microfarads. This is the biggest I could find at good enough voltage. That's why I put this voltage to show what I have, basically. But I have bigger capacitors, but at a very low voltage, like 10 volts, 6, very, very low voltage. And I managed to find a couple of this, let's say, higher voltage. They are all scrapped, and they should be okay. And you could see is a clear oscillating line. So right now, let me change that 3,300 microfarads with this one with 1,000 microfarads, like I had it originally, actually. This is with 1,000 microfarads, this one, and this is the waveform, and you see it's hairy. It's having a little bit of hair on top there, and squiggly lines. And if I'm changing from here, it's not really changing anything like that. You see, that's the zoom in, but actually this waveform was a little bit different. That's why I mentioned it, and that's why I'm mentioning these capacitors, the value of them, because I got a very, very different waveform inside that wave. Let me show it again, actually, and turn off my transformer here. So I freeze the image. I was getting, for each little strand of spike, I was getting a very clear line to the negative here, like that, to this line, until this, like that, and it was like full of vertical lines. But this one that I'm having here is not showing that. Now I'm starting to question how good is this oscilloscope after all, this Fenirsi. But to be sincere and to be correct, I did made a lot of experimentation, and most probably that specific waveform, when I was having this 1,000 microfarad here, I took that picture when I was having these two bridge rectifiers, and most probably I'm thinking right now out loud, maybe the voltage, if now is 7 volts there, back then it was 5 volts, and probably the voltage was too low, and it kind of created some sort of delay, enough delay to see the spike down to the negative, to the 0 volts rail. That's my interpretation. Probably it's not it, but that's what I got. So that's one problem. Another problem is that I'm getting this ondulatory waveform. Let me actually power it. Top it again, like that. I really like it. They are very cute with this little hair on top of them, you know. A bunch of hairy waves. This is the professional naming of these waves. They are called hairy waves. All right, so it's exactly like before when I didn't test with the MOSFET. Is, if you are watching here, this minimum voltage is plus 444 millivolts, but it's not under 0 volts. It's not negative. So it's, you can also see it here. This marker, this yellow marker, is actually the 0 volts marker. And imagine a line here of 0 volts line. And this is way over that 0 line, is this value, this 444 millivolts over the 0 volts. And this is the maximum. This is voltage peak to peak between these two. The hertz is 120. It's doubled from when I inserted this resistor directly with that black wire directly to the negative, when I put it directly, when it wasn't switched. Right now, this waveform, this hairy waveform that we are seeing there, is actually switched by this transistor here. And also this resistor, that's why I'm plugging out this transformer, because this resistor is very hot. It's quite hot. In a couple of seconds, it's getting very, very hot. The transistor is actually doing what it is supposed to do. It is switching and not overheating like I had in other experiments before. So I believe what I'm having here is a correct and by the book switching circuit. But what I'm using here, this is my problem here, and nobody can help me with this little detail. It matters what loading I'm using, what testing load I'm using. And in this particular case, with what I'm working here, I'm using this 1 ohm load. So it matters what I'm powering with this switching transistor that I'm having here. And I'm not powering electromotive element that is spinning, you know. I'm not powering, I don't know, something that requires big amount of power. And this guy is not actually delivering too much power in itself, but it is absolutely good enough for my experimentation that I have to do. This small power transformer that I'm having here, it is capable of heating up this 50 bloody watts resistor in a matter of seconds, in about 5 or 10 seconds of running. It is capable of heating it up, and if I'm leaving it too much, probably even burn it. But of course, I'm only using a couple of seconds of experimentation, what I'm doing usually. When I'm uncertain of a couple of variable elements that I'm having here. When I'm certain of stuff that I'm experimenting with, and I'm doing it intentionally, I can test for a couple of minutes, like tens of minutes, 10, 20, 30 minutes, and maybe up to an hour. But that's very different circumstances. Here, what I'm having are variable elements. I'm changing them, like that capacitor, like this resistor, and also I changed a lot this voltage that it is coming from the transformer. Before my last movie and this movie, I'm having very different voltage outputs. So this is a variable also, the output of this transformer. So I'm keeping, the idea is to keep it short. You test, you look, you catch the data, you note it down, you record the data, and you are literally, at least I am literally forced to draw some sort of conclusions after I'm making an experiment, because if I'm not drawing any conclusions, that experiment is dead, and I am doomed to repeat it in the future. So I am forced to put a diagnostic if it's better or worse than before. Usually I'm trying to find the little shits like this, and probably that, little shits, little problems that are creating problems. Usually I'm trying to find, this is what I am concentrated on, how to make it better, how to get the result that I need it to get, how to get the best result that I can get from the experimentation. It's not always the case, but that's my mentality, how I'm thinking and how I'm seeing things, and how I'm experimenting. I'm trying to find a better solution and a better response and a better reading than my previous experiment that I had it before. I'm trying to snipe when is better and pay attention when is better. And when I see a hint, yes, now it's a tiny little bit better than before, I'm trying to step back a little bit and look around and see what the hell I changed now when it's better from when it was erroneous or bad. So basically that's my thinking and my methodology that I'm using here. So I believe, but I'm saying it with half a mouth right now. I believe this experiment that I'm having here is actually a good experiment and a finished experiment, and it's not failed. It's actually is not a failed experiment. Right now what I'm having, the transistor didn't got hot at all, only the load resistor, and also the transformer remained cold, but on the long run I didn't test it, so I cannot say if the transformer and the transistor on the long run, if this experiment is okay with them running very long time. But for a quick test that I did here, it pops out that this resistor is taking all the heat, literally, and these two elements are remaining cold. This is actually filtering good enough, 1000 with a hairy waveform. I will change it back with the 3000 because I don't have a 4000 one. I can probably put in parallel these two, 1000 and 3300 microfarads like this two, but it will be very ugly, and I will leave only this for filtering here. But even if it's a little bit hairy waveform, it's depends on the load. So I'm calling this experiment, what I'm having here, a success with the results, with the waveforms that I recorded. I would say this is a correct and a good success on this particular switching circuit, which is, by the way, is the first time when I'm doing this, when I'm switching a MOSFET voluntarily, when I'm concentrating explicitly on switching the MOSFET, not when I'm taking a circuit diagram from wherever, and yeah, it's doing its job fine, and it's doing all the powering is already thought and tested in time by engineers and time itself, and I'm just using, I'm not right now with this circuit that you are seeing here, all this mumbo jumbo that you are seeing here is the first time for me experimentation, and is a total novelty for me when I'm concentrated on something that is literally brand new for me. My biggest wish is to actually power, with this circuit that I'm having here, to power a load that requires a certain power dissipation, or a certain power consumption to run optimally, like a motor, or probably, or I don't know, I really don't know, or a heating element that is heating up to a certain value. And theoretically, I didn't test too much of this circuit, what I'm having here, but theoretically, if I'm changing the duty cycle on the gate, we should see here on this power line, we should see a decrease or increase in wattage on the load there. And if I'm using a heating element or an electromotor, we will see the changing in speed, or if it's heating element, the temperature that is creating, and probably some power LEDs. We will see in the future if I will come back to this specific pulsing MOSFET circuit that I'm having here. But I learned a lot that it is at very low resistance load, is actually pulsing the power supply itself. It is supra-soliciting it, is pulsing it, is like requesting from the power supply a little bit more than it was designed to deliver, and the way it should deliver. And I believe this is the safest way, at least for this experiment that I'm doing here with very low resistor load, and this very brutal switching to the ground, most probably. This is the safest way, in my mind, at least. I'm not sure how many others will do it, but this is the way I'm thinking is the safest. Yeah, this is actually a partial experiment, which is a partial successful experiment, what I'm having here. Because I didn't test everything that I wished for. There are many points to cover, and I didn't cover too many points. I covered only specific points and what I thought. And I also had a lot of problems to solve in the same time. Yeah, this is it about this little experimentation, this little circuit, this pulse PWM with a comparator. Very interesting circuit. And I want to say I learned something. I learned something else. Totally different from the main subject, the actual MOSFET that I wanted to learn about. I learned about its driving gate, about its power supply, a lot actually, about the load that I have to deal with it. But the actual MOSFET, I didn't test it for power. I didn't test it for maximum power that he can drive. I didn't test it for many other things that I could test it. I kind of orbiting around the MOSFET and fixing other stuff that make him not heat up. Actually, it helped not to blow up. I wish I could concentrate a little bit more on actually testing the hell out of it and actually reading some values and calculating some stuff and getting an idea of how of the performance that I'm having from using it. You know, right now is an undecided experiment. It's not complete at all. It is a successful one, but not completely 100% that I'm satisfied. So I am an unsatisfied experimenter with this circuit. That's it. That's it from your favorite artist electronics, Mr. Q12 here. Bye bye for now. Bye bye.